Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. I've been a chemistry teacher for 25 years, and I think I've found a way to try to help students learn chemistry in the easiest way possible. In today's video, we're going to be talking about limiting reactant and percent yield. And when it comes to stoichiometry problems, limiting reactant problems tend to be one of the most difficult types of problems for students to understand. So please watch this video from the beginning to the end so that you can become a pro at doing limiting reactant and percent yield problems. In this particular problem, we're going to be reacting iron with oxygen to make some iron oxide. What makes a limiting reactant problem special is that instead of given one reactant, you're actually going to be given both of them. In this case, they're going to say, what if we started with 2.37 grams of iron and 1.51 grams of oxygen? So I like to put my givens in the boxes, okay? And what they want to know is, well, how many grams of iron oxide should be produced? And it's like, well, I don't know what to do. Do I start with this one as my given and convert it over to iron oxide, or do I use this one, okay? The answer is you're going to have to do both, and then you're going to compare. What's going to happen is that one of these two, okay, are going to run out first. And whichever one's out first, that one is going to be what we call the theoretical yield. So there's a lot of vocabulary in this, but let's go ahead and start with converting those problems over, okay? So we're going to convert this one over into grams of ferric oxide, and then we're going to convert this one over to grams of ferric oxide. So let's start out with the iron first, okay? So it's 2.37 grams of iron. And what I'm going to do is I'm going to set up the train track. I'm going to go from grams of iron to moles of iron to moles of iron oxide, and then moles of iron oxide into grams of iron oxide. If you don't know how to do this, you got to watch the previous lesson, okay? So here we go. Grams of iron into moles of iron. Moles of iron into moles of iron oxide. And then moles of iron oxide into grams of iron oxide. We're going to use molar mass here, 55.8 grams per mole. I got that off the periodic table. Mole to mole conversion is our ratio of the chemicals: 4 for iron, 2 for iron oxide, and then I need to add up 2 irons and 3 oxygens to get the molar mass of iron oxide. It's 159.6 grams per mole. And when I do this in my calculator, 2.37 divided by 55.8 times 2 divided by 4 times 159.6, I get an answer of 3.39 grams of the iron oxide. Now I need to do the same thing with the oxygen. I'm going to go from grams of oxygen to moles of oxygen to moles of iron oxide, and then moles of iron oxide into grams of iron oxide, just like I did here, okay? But instead of starting with iron, I'm going to start with oxygen, okay? So the way this looks, 1.51 grams of oxygen as a given, okay? And I'm going to go from grams of oxygen to moles of oxygen to moles of iron oxide, and then moles of the iron oxide to grams of the iron oxide. Molar mass here is 32 grams per mole. Mole ratio is going to be 3 to 2, 3 for the oxygen, 2 for the iron oxide. Same molar mass of 159.6 grams per mole. And when I do this math here, so 1.51 divided by 32 times 2 divided by 3 times 159.6, okay, I get an answer of 5.02 grams of the ferric oxide. And when you look at this, like, okay, well, how much iron oxide should be produced? Should it be 3.39? Should it be 5.02? Should I add them together? What do? I don't know, okay? And if you don't know that answer, like right now, It's because you truly don't understand what the trade tracks are doing, okay? You might be able to do them mathematically, okay, from the last unit, but you're not understanding kind of like what they fully mean. So what I like to do in class is I like to compare this chemistry problem to a recipe problem, because I said cooking kind of like really helps us really form good foundations in our head of what's going on here chemically. So I'm going to kind of do kind of like a what if right next door, okay? And that's going to be about making turkey sandwiches, okay? And give me a little bit of liberty here. Make sure you hear the whole story here. So if I had 2 slices of turkey, okay, and 1 piece of bread, I could make a sandwich, okay? And now, as far as chemistry is concerned, 1 sandwich would be a turkey and 2 pieces of bread. So a TB2 is basically a turkey sandwich, okay? So that's kind of set up here. I got a balanced chemical equation, and I have a balanced chemical equation over here. Now let's work with 2 givens, okay? Let's say I had, 5 slices of turkey and 6 pieces of bread, okay? So those are my givens, just like these are the givens. And if you do a little bit of thought process here, based on having 5 slices of turkey, you might say, hey, you can make 5 sandwiches from 5 slices of turkey, okay? And then based on the bread, if I have 6 pieces of bread, well, if there's 2 pieces of bread per sandwich, then if I have 6 pieces of bread, I can only make 3 sandwiches, okay? So if I have 5 slices of turkey and 6 pieces of bread, how many sandwiches can I make? Well, all I'm doing is comparing these two, and I'm selecting the lower of the 2, okay? And whatever's the lower of the 2 is what we call our theoretical yield. This tells me like how many sandwiches I theoretically should make if I had 5 slices of turkey and 6 pieces of bread, okay? Let's take that over here, okay, to our chemistry problem. Well, when I compare these two, the lower of the 2 is this guy right here. So we're going to call that the theoretical yield. What this means is after 3.39 grams of iron oxide is made, this reaction shuts off. Just like after 3 sandwiches are made, the reaction shuts off. And the reason why I can't make more than 3 sandwiches if I work backwards, it's because the bread is running out, okay? So the bread, okay, is kind of like what we call the limiting reactant. And what the limiting reactant does is it controls how far a chemical reaction can go, because as soon as it's consumed, the reaction shuts off. As soon as there's no more bread, you can't make any more sandwiches. So let's kind of look at our chemistry problem, okay? This one was the lower of the 2. After 3.39 grams of iron oxide is made, the reaction shuts off, okay? Why does it shut off? It's because we consumed all of the iron. So the iron here is what's called the limiting reactant, okay? As soon as all of it's consumed, you can't make any more iron oxide if there's no iron, okay? So iron is going to be called the limiting reactant, okay? Well, what do you call the other reactant? Well, over here, okay, after the bread is all used up, we know of the turkey that some of the turkey was involved in making sandwiches. However, there's 5 slices of turkey here, and after 3 sandwiches are made, some of the turkey was used, but some of it was unreacted. And the same things that's true over here, okay? Whichever one's the larger of the 2, this is going to be the oxygen. We know that some of the oxygen reacted, okay? But some of it is unreacted. So we give this the name reactant in excess, okay? Which means that there's going to be some left over, okay? In the case of my sandwiches, okay, after I make 6 pieces of, after I use the 6 pieces of bread to make 3 sandwiches, I use 3 slices of turkey, okay? So it means that 2 slices of turkey are left over. Now, I need to come back and show you how to do that in the chemistry problem. So let's erase the turkey sandwiches for now. And what we know right now is we got 3 vocabulary words by converting both of these over to the common product, okay? Whichever is the lowest of the two is what we call the theoretical yield. When you work it backwards, we find out one of the reactants is going to be a limiting reactant. In this case, the iron is the limiting reactant, and the other one is called the reactant in excess. So we have three vocabulary words: theoretical yield, limiting reactant, and reactant in excess. Got two pieces of this problem that are left, okay? One piece is to figure out, well, how much of the reactant in excess is left over? Or in other words, how much reacted and how much did not react, okay? To do this, what we're going to do is we're going to take our limiting reactant and we're going to convert it over to the reactant in excess, okay? So since all of the iron is reacting, we want to figure out, well, how much of the oxygen is reacting. So we're going to take our limiting reactant, which is 2.37 grams of iron, and I'm going to convert that over into oxygen. So here we go. Okay, we're going to go from grams of iron to moles of iron. Moles of iron to moles of oxygen. And in moles of oxygen into grams of oxygen. Okay, 55.8 grams per mole. The mole ratio between iron and oxygen is 4:3. 4:3. And then the molar mass here is going to be 32 grams per mole. Okay, and when I do the math here, I'm going to get an answer of 1.02 grams of oxygen. Okay, this amount tells you if all of this iron reacts, this is how much oxygen is going to react. And if we know that 1.02 grams of oxygen reacts, and we started with 1.51 grams of oxygen, then we can figure out how much did not react simply by subtracting the two. So if we started with 1.51 grams of oxygen and 1.02 grams of oxygen reacted, then the difference between those two, which is going to end up being 0.49, terrible 9, try that again. We know that 0.49 grams of oxygen is unreacted. Okay, so 3 train tracks here. We got 2 train tracks here to decide which one's the theoretical yield. This is how much iron oxide should be made. We know that the limiting reactant is completely consumed. There's nothing left over of the iron after the chemical reaction. We know that 1.02 grams of oxygen reacted, which means 0.49 grams of the oxygen did not react. So when this reaction's all over, 0 grams of this is left over. We're going to have 0.49 grams of this left over, and we made 3.39 grams of the iron oxide. Okay? The last piece, okay, of doing all this is figuring out this concept called percent yield. Okay? And the way percent yield works, I got a little room left over here on the board over here. Let's kind of like block it off. Okay? So percent yield is basically like a grade. It tells you like how good you did in a particular problem. Okay? For example, if you have a quiz that you got a 9 out of 10, you can calculate that into a percentage. 9 out of 10 would be a 90%. Well, this is done no differently. Okay? The numerator is going to be kind of like what you get in your experiment. And sometimes we call that an experimental yield. Okay? The denominator is what you should have gotten if you were perfect. Okay? In this case, it's going to be your theoretical yield, which is 3.39 grams here. So the denominator is going to be theoretical yield times 100. So if I was taking a quiz where I got a 9 out of 10, I got a 9 in my experiment. I should have gotten a 10. 9 divided by 10 is 0.9 times 100. That would be a 90%. Okay? In this case of percent yield, okay, you would actually have to perform this experiment. Okay? And if I perform this experiment with exactly 2.37 grams of iron and 1.51 grams of oxygen, I did the experiment, okay, I would then have to measure that iron oxide. So the only way you can get experimental yield is if it's in the prompt of the problem or if you physically do the experiment, okay? So let's kind of pretend that I actually did this experiment, okay? And then when I did the experiment, I ended up making 3.18 grams, 3.18 grams of the iron oxide. Now, like I said, I would have to physically do this or it would have to be in the prompt of the problem, okay? Well, if I make 3.18 grams of iron oxide, but I should have produced 3.39, well, what I'd have to do is I'd have to divide those two numbers, okay, and multiply it by 100 to figure out how good I was in the experiment. And if you take 3.18 and divide it by 3.39, okay, you'd end up getting 93.8%. Okay, so remember, this number right here, experimental yield, that's a number that you'd have to actually get in a prompt of a problem, or you would physically have to do an experiment. The bottom number, however, is what we figured out by converting both of our reactants into a common product and choosing the lower of the two. Okay, so that's how you do limiting reactant and percent yield problems. Okay, if you found this helpful, please do a like and subscribe. Even leaving a comment will really help. And I'm going to do another problem just like this, okay, in another video. So if you want extra practice, look for that next video.